Good morning, class. Welcome to Tuesday, June the 9th, 2020, Coronachem, day 44, period 1. I asked you some pretty tough questions for your level yesterday in a mock test, and I'm going to solve them for you. And I encourage you to pay attention to every step and try to understand every discrete step that we're going to go through today, because it comprises just about everything you need to understand for grade 11 and to have an easier time next year when you do grade 12, and also eventually if you go to university and enter some kind of scientific study, you should be somewhat familiar with the things that happen here. It's going to build up your intelligence. It's going to make your further education easier. Will you ever use any of this stuff? Probably not as much as we're doing, but that's not the point. The point is you're putting your brain through a process that is going to increase your capacity for problem solving, and that's why we're doing it. So I recommend you pay attention carefully, try to understand every single step. If something grasps you as not completely clear, stop the video, back it up, and watch it again, or else go watch some other video where I'm doing the same things. I have a stoichiometry playlist that you can watch with some 20 videos in it. Don't give it up, because once you get it, you'll find that the pattern repeats itself in all the other problems that you do in chapter 3 and 4. So the first question I assigned was 94 from chapter 3. I'll read you the question and then we can solve it together.
It says a chemical plant uses electrical energy to decompose aqueous solutions of sodium chloride to give chlorine, hydrogen, and sodium hydroxide. They give you the balanced equation up here. 2 sodium chlorides, 2 waters combined to give you 2 sodium hydroxide, hydrogen gas, and chlorine gas. The question asks for part 1, if the plant produces 1.5 times 10 to the 6 kilograms, or 1.5 million kilograms, or 1,500 metric tons of chlorine daily, estimate the quantities of hydrogen and sodium hydroxide produced. So the first part, we're going to solve for how much chlorine gas is produced. So we start off with 1,500 tons, 1,500 tons of the chlorine gas. So let's convert that to a gram quantity, because our molar masses are expressed in grams per mole. So 1,500 tons times 1,000 kilograms per ton times 1,000 grams per kilogram. All the units except grams cancel, and you're left with 1.5 times 10 to the 3, which is another way of expressing 1,500, because 10 to the 3 is 1,000, and 1.5 times 1,000 gives you 1,500. 10 to the 3 is just another way of saying 1,000. So 1.5 times 10 to the 3 times 10 to the 3 times 10 to the 3 gives you 10 to the 9. That's how many grams of chlorine you're producing. Now let's find out how many moles of chlorine that is. So chlorine has a molar mass of 35.45. Remember, it's a diatomic element. Diatomic element. So 2 times the molar mass gives you the molar mass of chlorine molecules. And there is a 1-to-1 ratio. 1 mole of hydrogen is produced also at the same time as 1 mole of chlorine gas. In this reactor, see, there's a 1 here, there's a 1 there. You don't write the ones, but it's understood. So that means you're going to produce 2.115 times 10 to the 7 moles of hydrogen. You see how, where did I put the marker? You see how grams of chlorine cancel, so you're going to have moles of chlorine, and moles of the chlorine is actually here in the numerator because it's in the denominator of the denominator. So it's going to cancel with the moles of chlorine gas, and chlorine also cancels. So what you're left with is moles of hydrogen. That doesn't cancel. You have that many moles of hydrogen, and you're going to multiply it by the molar mass of hydrogen gas. Why do they multiply by 2? Because hydrogen is a diatomic element. Remember Hofbrinkel, you know that. And you get 4.26 times 10 to the 7 grams of hydrogen gas.
and then when you report it, you're going to say 4.3 times 10 to the 7, or 43 million grams of hydrogen. A more practical unit is to divide it by a million. There's a million grams per ton, and you get 43 tons of hydrogen produced from 1,500 tons of chlorine gas. Chlorine is a much heavier element. That's why there's such a huge discrepancy. Hydrogen gas is very light. Now, to calculate the second part of the problem, they're asking you to see how many grams of sodium hydroxide is produced, or how many tons. So again, I forgot to write down how many moles of chlorine gas was produced. So I have to redo that part of the calculation, no big deal. So I did that here. And then, but now I included the molarity between sodium hydroxide and chlorine gas. So for every 2 moles of sodium hydroxide that's produced, only 1 mole of chlorine gas is produced. That's what that 2 to 1 means. All right, so again, we can cancel the grams. The moles is actually in the numerator because it's the denominator of a denominator, so it cancels with this moles. It also cancels chlorine. So what you're left with is moles of sodium hydroxide. That's how many moles, when you multiply all the numbers out, this divided by that times 2 divided by 1 doesn't change anything. So this is what you get, 4.23 times 10 to the 7, or 42 million moles of sodium hydroxide. Then we multiply by the molar mass of sodium hydroxide, which is comprised of sodium, oxygen, hydrogen. Those are the molar masses of those 3 things, in units of grams per mole, which causes moles to cancel, so you're left with grams of sodium hydroxide. We report it to the correct number of significant figures, which is 2. So 1.69 turns into 1.7 times 10 to the 9. Converting from grams to tons is more practical here. There's a million grams, 10 to the 6 grams per 1 ton. So the grams cancel, and you get tons of sodium hydroxide. So you get 1.7 times 10 to the 3, or 1,700 tons of sodium hydroxide from that much chlorine gas. And that solves our question. Let me just make sure yeah, we've answered all the parts that it was asking. The next question I asked you to do was question 100. This is also, I'm not going to say a hard question, but it's a long question because it has many parts, and it asks you to solve many steps. So again, I ask you to do not accept that there's some step you don't understand. If there's even just one step you don't understand, struggle with it. Because it's like, if you have one step that you don't understand in the solving of the problem, it's like having a chain with one weak link. The chain is only as strong as the weakest link. So when you pull on the chain, it's going to break on that weak link. So you need to know all the different parts of your chain have to be strong. At every step, you have to know what's happening. Don't accept ignorance in the solving of these problems. And it's not extremely difficult. It just is a series of steps, and you keep on recycling the same steps. So learn those steps, and you'll find that the problems are really not that hard. They're just maybe tedious. For example, this one fills a whole page. So I may have to erase a couple times before we get through this whole problem. Let's read what it says. So problem 100 asks, aspirin, C9H8O4, is produced from salicylic acid, C7H6O3, and acetic anhydride. A. How much salicylic acid is required to produce 150 kilograms of aspirin, assuming that all of the salicylic acid is converted to aspirin? Let's visualize what's going on here. This is not absolutely necessary to the solving of this problem, but it's nice to see what's going on. I hate being in the dark. This is what salicylic acid looks like. It comes from the bark. It was first discovered in the bark of willow trees. The word for willow is Silicic in Italian. So salicylic acid is a derivative of the willow tree. So a lot of plants have substances in them that have medicinal properties. Acetic anhydride looks like this. It's basically 2 molecules of acetic acid stuck together and water taken out of it. So it's called an anhydride. They take water away from it. So you don't have to write this part. This is just to show you what the chemical reaction looks like. When they make aspirin, they use this reaction to make it. Alright, so this is called salicylic acid. Comes from the bark of willow trees. This is called acetic anhydride. And this is called acetyl salicylic acid, also known as ASA for short. Acetyl salicylic acid. It's aspirin. That's aspirin. And see, you see they start with this molecule and they stick this piece over here. So they take away the H and they stick a part of this molecule on there to make this molecule do a chemical reaction. And they made one of the most popular anti-inflammatories and antipyretics, meaning it reduces pain and inflammation. It also reduces fever. It's got also a lot of side effects. It's a dangerous drug, really, if you take it for the wrong dose, or if you take too much of it, or if you take it for too long. It has all kinds of side effects, but it's actually quite effective for lowering fever and reducing pain on many things. I remember once I had the nail on my big toe was actually coming off. I had a huge bruise on my toe because I was skiing so much, and every time I landed a jump, I was landing on the tails of my skis, and my toes were coming up, and they were touching the top of the boot. And I did it so many times that I got a bruise on my toe. My toe was killing, so I took 3 aspirins that morning so I could go skiing, and the inflammation went away completely. I was able to ski the whole day without any pain. I was amazed by how effective aspirin was for me. It might not work for other people, but for me it works very well. But you have to be careful not to take it too long, because then you get stomach pains, you get ulcers from it if you take it too long. Anyhow, let's call this SA. We'll call this AA for acetic anhydride. So it took the first letter of each one, and we'll call that ASA. It's just going to simplify the doing of the problem. So let me erase now. So I'll show you the actual formulas with the number of elements of each, because we have to do calculations on molar mass. So this is SA, the salicylic acid. Here's the acetic anhydride, the AA. And they react to form aspirin, C9H8O4 plus the acetic acid, which is a byproduct that's left over after you react the acetic anhydride. Yeah, we'll call this ASA. The molar mass of this one is 4 times 12.011 plus 6 times 1.00794 plus 3 times 15.394, and it's going to be in units of grams per mole, obviously, and what you're going to get is 102.08984 grams per mole. The aspirin, of which there are 150 kilograms, of which there is 150 kilograms, is 150,000 grams, and we're going to divide that by 9 times 12.011 for the carbon, plus 8 times 1.00794 for the hydrogen, plus 4 times 15.394 for the oxygen, and that's going to give you a molar mass. I'm putting a line under it for it. It's going to give you a molar mass of 180.16012 grams per mole. We're going to need that later when we do our calculation. So we have the acetic anhydride and we have the aspirins. 150,000 grams divided by 180. Let's find out. Moles ASA needed at the end is 150,000 grams over 180.16012 grams per mole. equals 832.592696. 5926, sorry. 592696 moles of ASA. Because the stoichiometry is 1-to-1, you're going to need the same number of moles of SA. So 832.592696 moles of salicylic acid is needed because of the 1-to-1 ratio. So that means, and I wrote that down, actually I should write that down. So ASA times 1 mole of SA for every 1 mole of ASA means I will still need 832 point blah 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 moles of SA. Keep all your numbers in your calculator during the calculation. Never round off during the calculation. Only round off when you present your last answer. So then we're going to multiply by the molar mass of salicylic acid, which happens to be composed, I'll do that up here, and then I'll write that number here, because otherwise it's going to get too cluttered. Well, it's going to get cluttered anyway, but at least we can see what we're doing. 4 times the molar mass of where did I put the molar mass of salicylic acid? Sorry, yeah, it's not 4, it's 7 times 12.011 plus 6 times 1.00794 plus 3 times 15.394. What you get in grams per mole is 138.12284 grams per mole. So we have 832 moles of salicylic acid multiplied by 138.12284 grams per mole means you are going to need 1.15000068 times 10 to the 5 grams of salicylic acid. Let's convert that to a more manageable number. There is 1 kilogram for every 1,000 grams, and therefore you're going to have 115.000068 kilograms, and then of course when you report it to the proper number of significant figures, you can have 115 kilograms of SA. So you need 115 kilograms of salicylic acid to generate 150 kilograms of ASA. Now part B asks,
how much salicylic acid would be required if only 80% of the salicylic acid is converted to aspirin? So if only 80% of it is converted, you have to use more of it to get the same result. So let's show how that works. Erase all that.
Nice thing about videos is you can always back up to see what I wrote. Can't do that in the classroom because people, when I erase in the classroom, everybody yells because they haven't finished copying. B. So you have 115.12340068 kilograms of salicylic acid, and you only have 0.8 efficiency, right? Turn the 80% into a decimal, it's 0.8. So you're going to actually need 143.750085 kilograms of salicylic acid. So you have to, because you only have 80% efficiency, you have to use more of it, and that's how you find out how to use more of it. Because if you take that number and multiply by 0.8, you'll get that number. So we start off with 143 kilograms of salicylic acid at only 80% efficiency. It's as though you had only 115 kilograms of salicylic acid working at 100% efficiency. So that's how you do that calculation. With sig figs, you're only allowed 3 in this case, so 144. I know there's only 2. At one point it says 1.5.
times 10 to the 2, and then, but everything else is 3 sig figs, so I just kind of ignored that 1.5 part. I know, okay? So 144 kilograms of salicylic acid is necessary at 80% yield for the reaction. So if your reaction only gives you 80% yield, that's how much you have to use to get the result you wanted. Part C now. C asks you, what is the theoretical yield of aspirin if 185 kilograms of salicylic acid is allowed to react with 125 kilograms of acetic anhydride? So let's find out how many moles that is for each one. So if you have 185 kilograms of salicylic acid times 1,000 grams per kilogram, divide all that by the molar mass we found earlier, which is 138.12284 grams per mole. You're going to get 1,339.38746 moles of salicylic acid. Also, if you had 125 kilograms of acetic anhydride, again there's 1,000 grams per 1 kilogram. Divide all that by the molar mass of acetic anhydride, which we found out earlier in our previous calculation. It turns out it's 102.08948 grams per mole. So that means you have 1,224.41175 moles of acetic anhydride. Now, what did I say here? It's a 1-to-1 ratio in the reaction, so this is the limiting reactant because it's got fewer, there's less moles of it. So AA is the limiting reactant. And the same number of moles of ASA is produced. Okay? You're going to get that many moles of ASA if there's 100% yield, which we're assuming. So let's continue our calculation. Again, I actually feel bad erasing it because I'm used to not erasing when I'm in the classroom. I actually have to do violence to myself to erase the board right after I write it because I know normally kids would just freak out if I did that. So we had 1,224.41175 moles of AA. That's our limiting reactant, and we know that the ratio is 1 mole of ASA produced for every 1 mole of AA reacted. So we're going to get 1,224.41175 moles of ASA. Now we multiply by the molar mass of ASA, which happens to be 180.16 from our previous calculations, which means we will get 2.2059068 times 10 to the 5 grams of ASA. Convert that to a more manageable number. 1 kilogram for every 1,000 grams means that you will end up with 220.590168 kilograms. You're not going to report that number. You're going to report 221 kilograms of ASA as your final answer to 3 sig figs. Although if you were to insist on writing 2 sig figs, I couldn't really mark it wrong because there is actually one of the figures in there is only 2 sig figs. So if you did it that way, I would accept both. Because in industry, it's not like they're going to sit there and go, oh, you used the wrong sig figs, you're fired. You might end up wasting a little bit of material, but it's not that important in this large industrial process. So in part D now, it asks, if the situation described in part C produces 182 kilograms of aspirin, what is the percentage yield? Okay, so you had 182 kilograms. Suppose you had actual yield of 182. Instead of getting the theoretical yield, you actually got that, which is less than what you expect, which happens in real life. You don't actually get
100% everything working out perfectly. There's always side reactions, stuff gets wasted, you know, you did it at the wrong temperature or whatever. Things happen, you always get less than your theoretical yield. And if you get more than your theoretical yield, it's gone even more wrong because you've probably got some contamination. So 182 kilograms divided by the 220.59, use the full unabridged number when you're doing your calculation as always, times 100 gives you 82.505. This is what you're going to get in your calculator readout, 9436%, and then what you're going to report is 82.5% yield. And that concludes that question. How much time have we used? Because I think we're going to need more. Oh, we're at 25 minutes. We don't have enough time to do the next questions because they're big questions. So, you know what I'm going to do tomorrow? We're going to cover the other two questions for this mock test. Just tonight, focus on understanding what you did here. Okay? Try to reproduce these answers. First, look at my solution. See what I did, and then try to reproduce the answers on your own. There's two questions. If you didn't already do it on the mock test, now is the time to learn, because I'm going to test you not tomorrow, but the day after tomorrow. So here's your chance to really prove to me that you learned the material and do a good job, and we'll talk tomorrow.